Okay, so let's start from the error correction code. So last time we talked about five qubit code, and we talked about how 5 qubit code could correct an error on one of the 5 qubit. So you need basically 5 physical qubit to encode one logical qubit. Now we are going to talk about, there are lots of quantum error correction code. We're not going to talk about all of this. We're going to talk about what's the principle underlying these kind of error correction code. And then we jump on to introduction to the surface code. So the principle of error correction code is the syndrome measurement. So what is syndrome measurement? It basically detects an error without changing the qubit state on the data qubit. So basically there's a ancilla qubit and data qubit. And data qubit. And you only take the measurement on ancilla qubit. I don't know how to translate ancilla in Korean, but anyway, so ancilla qubit is the only way you can detect, only channel that you can detect whether there was an error occurred at the data qubit. You don't do anything on the data qubit, nor you alter the qubit state on the data qubit. So it's measure the ancilla qubit to detect the data qubit, detect the error on the data qubit. So I'll give you the easiest example of this syndrome measurement. So we have, let's see, 2 qubit state. So this is ancilla. And this is data. Suppose they are initialized at cat0 at the beginning. Let's try to compute how the quantum state changes over this circuit. So let's see, 0, 1, 2, 3. So psi 1, let's start from 1, is plus 0. So I'm taking maybe opposite. So I'm taking the first qubit to the top, as a top one. So 0 tensor plus. So this is ancilla and this is theta. And what's the next one? So depending on whether sorry, it's opposite, right? So this is theta and this is ancilla. Depending on the measurement, the state of ancilla qubit, you change the quantum state here. So it's 1 over square root 0, 0 plus 0, 1. So after applying C naught gate, it becomes to 0, 0 plus 1, 1. And then you apply Hadamard gate again. So psi 3 is 0 plus 1 minus. So it's going to be 1 over 2 of 0, 0, 0, 1 plus 1, 0 minus 1, 1. So now I'm going to combine this one with this one together and this one with this one together to get, let's see, 1 over square root of 2 times 1 over square root of 2, 0 plus 1, sorry, 0 plus 1, 0 plus 1 over square root of 2 of 1 over square root of 2, 0 minus 1, 1. Okay? So this is 1 over square root of 2 of plus 0, and this is 1 over square root of 2 of minus 1. Okay, so we have changed the state. Well, that's okay. Why? Because we changed the state of the theta qubit, which is the eigenstate of our x gate. So you can see that plus 1 is plus 1 eigenstate of x, and minus 1 and minus ket is minus 1 eigenstate of x. So what we do next is measuring the ancilla qubit. So we take the measurement at the end. So when you take the measurement, either the first state is observed or the second state is observed. So whichever we observe here, we still get eigenstate. Okay, so the thing that matters is we get an eigenstate. So after the measurement of the ancilla qubit, we make the theta qubit to an eigenstate of x. Okay, so let's suppose that I measured it and I read 0. So I read 0. That means it's fixed to the plus 1 eigenstate. And then after I measured it again. Okay? So if nothing happened, then I should read. So what I do is I go through this circuit again to the state where I changed it to eigenstate. So if nothing happened, then I should measure 0 when I measure the ancilla. Why? Because you see, this is already fixed to the eigenstate, and what it does when I apply this x gate is it doesn't change the state. It's the same state when I apply the x gate to the plus 1 state here. So nothing happens. Whether or not I take the C0 gate after Hadamard gate, whether or not the state on the ancilla qubit is 0 or 1, whether or not I apply the x gate or not, the theta qubit has the same state. So nothing happens. However, if something happens on the theta qubit, then I may read the ancilla qubit not equal to 1. What is that? If there was an error, that error, then I get change my, I get the different answer after I measure the ancilla qubit. So here, if there is an error, X error, sorry, Z error on the theta qubit, then the read of ancilla qubit is changed. Okay, let's see, let's compute this one. So what does that mean? So let's say I have fixed my state to be plus 0. So this is data and this is ancilla. Okay, so I feed this to, I feed these two, let's see, the same circuit here, X, H, and then measure this here. Okay? So what happens is I assume that there is unwanted Z gate applied in somewhere here. So let's see what happens. When Z gate is applied to the +1 state, then it changed to -1 state, right? So it at here, let's say this is 1, 1 here, 2, and 3. So psi 1 is now -1 tensor plus, and then this is, let's see, compute everything into superposition 0, 0, 1, 0, 1, 0, 0, 1, and -1, 1. So after I apply the CNOT gate, what happens is look at the ancilla qubit and apply the X gate. So 0, 0, and 1, 0, plus 1, 1, minus 0, 1. Right? And then we apply the Hadamard again. So psi 3 is 1 over 2, 0 plus, 1 plus, 1 minus, 0 minus. So I'm doing this tedious calculation just to show that this is actually works, but you can easily imagine that if you try to, you can done by theoretically, because what we have done before the last time is when you have that gate to this kind of simulation, switch the order of that gate to next gate, you get minus out. So right, so you can do the same thing with the that kind of operation. But let's finish this operation. So here you have, okay, 0, 0, 0, 1 minus 1, 0, 1, 1, and 1, 0 minus 1, 1, 0, 0 plus 0, 1. Okay. Wait, so it's yes, right? Right, yes. And then let's see, there should be some maybe not canceling out. So here we have canceling out, and here we have canceling out. So all the state of the ancilla qubit is 1, and there are twice of that. So we have 1 over square root of 0, 1 minus 1, 1. So wait, 0, 1. What did I say? 0, 1. So therefore, it's minus tensor 1. Okay. So you can see from the beginning, we had plus 0 in the beginning, but when there is that gate, or Z error occurred, then the read off should always change, should be 1, meaning that the data qubit is now changed to -1 eigenstate instead of +1 eigenstate. It was +1 eigenstate in the beginning, but because of Z, it became -1 state. And the important thing is we can detect the change of eigenstate by measuring the ancilla qubit, because the measurement outcome is now changed to 1 instead of 0 due to the existence of the Z gate, Z error in the data qubit. Okay, so this is the syndrome measurement. This whole circuit is a syndrome measurement that can detect whether there was Z error on the data qubit. So how do we detect an X on the data qubit? The same thing, because you can now change the role of X and Z and do the same thing. So when you have H, set here, H, and you take the measurement here. So you start from the initial state, 0, 0. At here, let's say it's 0, 1, 2, 3 stage. The precise 3 is becoming the superposed state of ancilla 0 and ancilla 1. So, and the data qubits are initial are stabilized to the eigenstate of Z gate. So what's the eigenstate of Z gate? It's either 0 ket or 1 ket. So it's either 0 tensor and or 1 tensor. Square root of 2, root of 2. So depending on the readoff of the ancilla qubit, you always fix your data qubit to be collapsed to the eigenstate of Z gate. So and then once you have the eigenstate of Z gate, then you can detect the next time you run the circuit again, you can detect whether X gate or X occurred on the data qubit because you do the same calculation. Then the readoff change it to 0 to 1 or 1 to 0. So again, in the previous example, I assumed that my first readoff of the ancilla qubit was 0. That's why I get 1 after having that error. But if your first readoff of the ancilla qubit was 1, then your data qubit is initialized to -1 eigenstate, which is minus. Then the final readoff after having that will be turned into 0. So readoff is changed to 1 to 0. That means there is that. So whenever you detect a change in the readoff, that means you have that. That's the basic idea of how the quantum error correction code, and still the only way people found as an algorithm to find detect them. So what do we do about this? So it's about how we design these ancilla qubit and data qubit somehow amalgamated together to make up the entire logical qubits. So I'll show you one of the example, which is the surface code. So before we move on, I want to fully understood what is going on in here. So when I do the syndrome measurement, I only take the one data qubit, one ancilla qubit. If you want to increase the number of data qubits, then you can just add more. So you can just add more numbers. Well, okay, so let's look at this one. So before I ask a question here, how about, okay, okay, so here I have two data qubits. So we have X and X. So this is ancilla, and these two are data qubits. Okay. So what happens here? When I take the measurement after this circuit, I can detect either 0 or 1. Let's say it's 0. Then what can you say about the state of these two data qubits? It's stabilized to what? Eigenstate of X, right? Eigenstate of 2X. So first X on the first qubit, second X on the second qubit. So you can say my gate is consists of two x's, x0 and x1. Let's say this is x bar. So I can make my 2-qubit state to be stabilized, to be an eigenstate of x bar by applying the circuit and take the measurement. Depending on the measurement, it's a +1 state or -1 state. Doesn't matter. It's just that. However, when you have this, the problem is, okay. So if I had one data qubit, if I read 0, it means I know that this data qubit, one data qubit, is stabilizing +1 eigenstate. But now I have two data qubits hanging on one end of the qubit. So if I read 0, it could be because of these two data qubits are stabilized to +1 eigenstate, +1 here. But it could be the result of being these two data qubits being a -1 eigenstate both. So that means a -1 times -1 +1. So they're also the same measurement. So when you apply more data, then there are more possibility of which one. So hard to figure out what actually happens on one of these data cubes. But if you just concentrate on the whole data quantum state on these two data cubes, then it doesn't matter, because if you're in a -1 quantum state, that's also +1 -1 eigenstate on these two data qubits. That's +1 eigenstate as a whole of this gate, which consists of two gates on the qubit 0 and 1. And also same for y. Same for when it happens at 1. It means either this one is +1 and this one is -4, +1 eigenstate. Okay? So keep this in mind. What we're going to do is trying to think about, can I increase? Well, we're trying to think about the surface code here. So, so maybe I'll make it smaller, not smaller, maybe 4. Okay, 4 is better. Okay, so I'll tell you what the left picture is. Just concentrate on the right picture. So this one, there are lots of qubits. All of these are qubits. Okay. The circle one is the data qubit. These are data qubits. And the square ones are antenna qubit. And it's called a stabilizer qubit. So we are taking the measurement on these square qubits, only on the square qubits. Okay? So I'll tell you what this x and z means actually. So what happens is, on these two qubits, no two stabilizer qubits are connected, and no two data qubits are connected directly. So all the data qubits are connected to stabilizer qubit, and there are sometimes one data stabilizer qubit or two data stabilizer qubit, but that's fine. But anyway, so we have one data qubit and one stabilizer qubit attached here. And what happens on each of these edge between stabilizer qubit and data qubit is the following. So let's say we have, erase this. Let's say we have X stabilizer and data qubit. So I don't put any information on data qubit because there are going to be some lots of entanglement and then superposition on the data qubits, but we don't care. What happens is, when I have this edge, that means I have, so let's see, I make a number here. So this is qubit 0. This is just a random number here. So just to distinguish the qubits in the circuit. So the data qubits, oh, I should make it opposite direction. So data qubit goes below, top. So this line segment connecting these two qubits, stabilizer and data, means that there is a circuit in between these two qubits, like this one, exactly like this. Okay, so when you have another qubit lying on here, so that means you have the same thing. So let's say this is qubit 2 instead. So then 0 and 2 also are having this circuit going on. But instead of X, we have Z, because we are talking about the Z stabilizer on the bottom, but instead of X stabilizer. So the label on the square qubit means that which gate we're applying on the C0 gate. It's the control gate here. Now, so we have these two stabilizer qubits attached to the data qubit. That means we have to take the same thing at the same time, right? So we have the same thing going on at the same time. So how to unite these two circuits? So what actually happens is you have data qubit and two stabilizer qubit. Yes, and here we have X, and here we have Z. And this is what happens. Okay? This is what's happening. So when I draw like these three gates and these three qubits in the picture like that, that means I have the circuit in between these three qubits like this. So this is what this diagram means. Okay. So when I run the circuit, actually it depends the order, but this is the right order. So you take the cinder measurement on X stabilizer, and take the cinder measurement on that stabilizer. That's what happens. So going back to the situation here. So for every data qubit, so think about you concentrate on one data qubit. Let's say concentrate on here. As I said, there's a big circuit going on, but just locally look at these qubits, the qubits that connected to these data qubits only. So then we have one data qubit attached to 4 separate qubits. So you have circuit having 5 quantum register. On the bottom, you have data qubit, and on the top, you have a 4 stabilizer qubit register. And depending on the value of these 4 stabilizer qubit, you have control X or control Z gate applied to the data qubit. So we apply our quantum syndrome measurement in this order. First, you take Z syndrome measurement. You take the Z stabilizer qubit circuit, and then you take the X stabilizer qubit circuit, and then you take the Z stabilizer. So you just follow this order, and you do it for every data qubit. So for example, when you do the Z stabilizer circuit, then between these two qubits, you do the same thing for any other pairs. So on the right side of the data qubits. So here, not this one. So when you do this, then you do the Z stabilizer circuit for this pair and this pair and this pair. Okay. So when you do the stabilizer circuit between these two qubits, then you do the same thing at the same time for this pair and this pair and this pair and this pair. Okay, so when you run all the circuits once, then you take the measurement on, you take the circuit between any two qubits connected by the edge. So you don't miss any of the circuits here. So that's what happens. So now, as I said, it's a syndrome measurement. After you run these circuit, like this one, after you run this circuit, at the end, you take the measurement on the stabilizer qubit, on here and there. So you read off the number, whether it's 0 or 1. Read off the number. What does it mean that it's 0? It means that it's a stabilizer. So you read the measurement, you take the measurement on this stabilizer, you get 0. That means this data qubit is stabilized to +1 eigenstate of that gate, and you read the measurement here, and you read 1, let's say, then it means that this data qubit, maybe actually not, it's a little bit complicated than that, but let's assume that we only take these two in consideration, that when you read 0 here, this data qubit is +1 state, and you read this one is 1, then in this data qubit is -1 state. Now that's when you just think about these two data qubits. But think about this. You have 4 data qubits, let's say in this stabilizer, you have 4 data qubits attached to the single X stabilizer qubit. When you read 0, it could be the result of -1 or -1. Let's say you read off the result of X stabilizer, the outcome was 0. Okay, that means it could be that these 4 data qubits are +1 eigenstate. The entire quantum state, the quantum information stored in these 4 data qubits has +1, is in the +1 eigenstate. However, if you just look at one single data qubit, it could be a -1 eigenstate, because if you have one more -1 eigenstate on one more data qubit, then -1, let's say -1 eigenstate, quantum eigenstate, -1 eigenstate, and +1 eigenstate, and +1 eigenstate of the X stabilizer, that gives you 2 minus and 2 plus, which gives you +1, and this could read off as 0, which means that this whole thing is +1 eigenstate of X stabilizer. So we can't really tell which eigenstate on single data qubits are according to the stabilizer qubit. But overall, you can say first it's the eigenstate of every stabilizer qubit here, and also at least you know the parity, odd or even number of these eigenstates based on the number read off at the stabilizer. So if your read off is 0, then there are only even number of -1 eigenstate, and if it's a 1, read off is 1, then you can tell that there are odd number of -1 eigenstate attached to that stabilizer. So that's basically the principle. So I'll show you the example here, how it works. I'm gonna make an error here. So as I said, there are 2 types of error. One is X and one is Z, and you can we say Y error when X and Z error occurred at the same time. So here on the left hand side, ignore the outside box here. So that's for other purpose, and just ignore this. There is no such real stabilizer here. Imagine. Ignore it right now. Here we can I simulating an error. So the error only occurs at the data qubit. So these colored circles are where the errors occur, and it indicates which error. For example, here x error, and here that error, and here x and y, x and z occurred at the same time. So think about what you would read after the error is occurred. If error x error occurred on this data qubit, as I said, when you take the syndrome measurement with x gate, you cannot detect x and x because x and x are commutable. So you can only detect x error when you use syndrome measurement with that gate. So your errors are detected on Z, which has a Z syndrome measurement. Okay? Now, if there is no other data qubit, no other things here, then because of this X error, you will read different outcomes on this set stabilizer and this set stabilizer. So what I mean by different outcomes is that first you take the circuit once and then read the circuit, and then luckily, let's say all the read off of these stabilizer are 0. Okay, and then after some time pass, and you run the circuit and then read all the stabilizer qubit again. Then because of this and no other error occurs, then only these stabilizers are changed to 1. The read off at this stabilizer are changed to 1. Why? Because X error occurs, you can detect the Z stabilizer or that syndrome measurement and detect an X error connected to the data qubit. So this one has the read of 1 because X error makes the eigen's +1 eigenstate of Z to -1. And same thing for here. So this one and this one are detecting an error occurred on this data qubit of X error. Now, the problem is there are more errors on more data qubits. So think about this one. This one has X error because it's a Y error. The X error makes the Z stabilizer to switch its read off. To switch the read off. Now, let's say all the read off of the stabilizer is 0 at the beginning. Now, because of this X error, it switched the read off here. And in here, there is X error and 2X error attached to 2X error on the data qubit attached to this Z stabilizer. So because of this X error, it switches the read off at this stabilizer. And also because of this X error, it switched the read off of that stabilizer here again. So you have double switch. That means you don't see any changes on this set stabilizer. So only the changes are detected in here and here. And look at this one. Let me explain all the others. Because there's a Z error, because it's Y error, Z error can be detected by X stabilizer, X syndrome measurement. So this can be changed. This read off at this stabilizer is changed. So we can detect that error. And because of X error, that stabilizer detects an error here, and not the X stabilizer can detect an X error. And because of the Z error is detected by X stabilizer, 2 X stabilizer connecting to this data qubit. And so this one is changed. But how about this one? So this is not changed because there is another the same X stabilizer. So they are double switch. So there are no changes in here. And look at this one, and that error is detected by X stabilizer right here, but there is also a Z stabilizer here, which turns the, the which changes the read of X stabilizer. So there's a double switch in here, so it turns off this read off. So it doesn't change the read off at this. So what we are doing here is assuming that we know that these errors here, and what will be the changes on our X stabilizer read off. But when we actually look at the real quantum circuit, real quantum machine here, we don't know where or which error occurred. So what all we can do, all we can detect is just where our read off are switched. So I think when I finish this explanation, I'll ask again if you don't understand what's going on. So here, I mentioned that why these four stabilizers are the only stabilizer that the read off not changed. So marked as yet red. And what you actually see in a real situation is only these stabilizer information that only these stabilizer have been changed its read off. Okay? We don't know where or which error occurred on the data qubit. We have to guess. We have to guess by looking at this result where error occurred on these data qubits. And then that might be our detection of an error. Now, if we are lucky, then we get all this exact same error here. But you can see that you can get the exact same result with different configuration of errors on the data qubit. This is not the only way. These data errors on the data qubit is not the only way you can get the same read off. So the problem is, it's not that you want to find out exact data qubits and exact errors, but you want to find the errors that is most probable that could happen, have this result, and then hopefully this guess, this most probable guess is the right detection of our error occurred on the data qubit. So there are more things to do in actual process of correcting the error, but for now, I want you to understand what's going on here. I want you to fully understand what's going on here. So I'll explain again from beginning if you don't understand about the syndrome measurement. It all depends on syndrome measurement. Error Y is the error X and Z. And Z occurred at the same. So let me start from beginning. So take this as an exercise. So let's say I have this. So initially it's all zero, initialized to zero. And after doing this, I take the measurement. Okay. So write the, so, let's see, this is psi, because this is ancilla here. Write the quantum state psi, and the read off is zero. Try to compute the steps, all the steps, and then assuming that your read off the top register C is equal to zero, what is the quantum state of the 2-qubit state, 2 qubits. So these two are considered as the data qubits. So you're trying to get the quantum state on the data qubit when your read off at ancilla is zero. 이거 X라 하지 말고 이거 Z라고 할게요. Z. 왜냐면 서비스 코드랑 연결해야 되기 때문에. That's Z instead of X. 2Z. 2Z. So what's the result? So when this is initialized to 0, 0, the data qubit 0, 0, then when C is 0, what's the quantum state? 0, 0, right? So assuming you computed everything here. So let's, in this case, think about this case. So do the computation for this. 1, 0. 얘가 제가 이거를 이미 저기 아이겐 스테이트 마이너스 원 아이겐 스테이트로 해놔가지고 얘는 무조건 1이 나오게. 아, 뭐 일단 계산하면 무조건 1이 나오니까 그걸로 된 거예요. 자, 그럼 어쨌든 대충 제가 계산하는 건 봤는데, 얘는 잠깐만요. 얘는 지금 얘는 이제 무조건 0, 0, 0. 그다음에 okay, so we have the result is after we take the quantum measurement. So that's an ancilla qubit here, right here. which is initially 0. And after taking this syndrome measurement, it becomes this one and this one. And it's 1, 0 again here. So what I want to say here is the measurement outcome of syndrome measurement right here, only 0 and 1, is determined by the quantum state on the data qubit, because 0, 0 is the stabilizer of 2Z gate on the 2 qubit state, and it's +1 eigenstate. And 1, 0 is -1 eigenstate. That's why we have a syndrome measurement 0 and 1. But this doesn't always the truth. So we could have any quantum state. We could have any quantum state stored in the data qubit. Whenever we take these circuit, and after taking the measurement, we make it into an eigenstate. So since we have already made an eigenstate, there is only one outcome, but that's fine. We already have an eigenstate, so we are going to get the same eigenstate before. But it doesn't matter whether we have the eigenstate before or we didn't have the eigenstate. Just taking the measurement, just taking this syndrome measurement entire circuit, running this entire circuit, makes your data qubit fall into the eigenstate of these two stabilizers gates here. So what we are doing here is actually that stabilizer attached to the two data qubits. Okay, so we have two data qubit attached to one data qubit. So this is, if I label by number 0, 1, 2, then this is qubit 0, which is on top of this circuit, and doesn't matter whether which one is left or right. It's the qubit 1 and qubit 2 on that are attached to the qubit 0, which is the ancilla qubit here. That's what we are doing. We take when we have this edge connected to data qubit to the stabilizer qubit, we are running the circuit like this. Whenever you have more data qubit, then you do more C0 gate or CZ gate in between its Hadamard gate, and then we take the measurement on the stabilizer qubit. Okay. So now, since we are familiar with what this is, suppose that my state in the beginning was 1, 1. What will be the measurement outcome? What will be the measurement outcome? Let's just 0. Why? Because 1 is already -1 state. So we have Z measurement. So it's going to be take -1 ket to -1 ket. And this one also take the 1 ket to -1 ket. So it's -1 plus. So it's a plus. So when you take this whole thing into what as a 2 qubit state, then this 2 qubit state is +1 eigenstate of these 2 Z gate. Okay, that's why we have a measurement outcome as 0. So this measurement outcome can detect whether your data qubit is in the +1 or -1 eigenstate, but it cannot distinguish which one is +1 or -1. It only can detect the multiple of eigenvalue, either +1 or -1, is +1 or -1. So there are 4 possible ways of getting the eigenstate. So for in the qubit 1 and qubit 2, it could have plus for Z gate and plus minus plus minus. But what you can detect after doing this circuit is either plus or minus, plus minus here. So that's a singular measurement. So in this case, you measure 0. In this case, you measure 1, 1, and 0. But that's fine because so first, as long as we take the measurement, all the data qubits fall into the eigenstate of that stabilizer, or in this case, that stabilizer. And even though we don't know exact state, exact eigenvalue of each data qubit, all we need to know is to find an error. Okay, we don't care what the state is, we only care whether there is an error. How can we detect an error? So if there was an X gate right here, let's see, on the qubit 1, let me give a different color here. So if there was an X gate, which is an X error here, then it changes the eigenvalue of the eigenstate. So let's say I had 1, 1 in the beginning, which is -1 eigenstate and -1 eigenstate. But after having X occurred, the data qubit 1 is now changed to +1 eigenstate of Z gate. So then what will be the readout? It will be 1, because qubit 1 is in the +1 eigenstate, qubit 2 is in the -1 eigenstate. So you change the readout. It was 0 because both qubit 1 and qubit 2 are in -1 eigenstate. So therefore you got +1 eigenstate as a 2-qubit state. But since we have changed the eigenvalue of 1 qubit, now we change it to -1 eigenstate as a 2-qubit state. So your readoff of your syndrome measurement is now changed to 1. So your readout changed from 0 to 1. So therefore, you know that there was one X error occurred either qubit 1 or qubit 2. Right? So not only qubit 1 makes the change, you could have the same change when you have an X error occurred on the qubit 2. So we don't know which one actually have an X error, but at least know that there is one X error either here or here. So there is also a limitation here. What if the X error occurred at the both data qubit? Then it changes the qubit state -1 qubit state to +1 qubit state, quantum state, eigenstate, right? So you don't detect a change on the readoff of the ancilla qubit, the stabilizer qubit. So then you might assume that there's no error occurred, but as I said, there actually 2 errors occurred at the 2 data qubits. Now, that's always there's always that kind of a limitation when you apply the error correction code, that if you have so many errors, then it actually ruins your algorithm to find the error. But if you have certain probability of physical error occurrence, then it has such a low probability that 2 errors occurred at the same time compared to 1 error occurred. Because if you want 2 errors occurred, then it's a p-squared. It's a very low chance than 2p, for example, like 1 error occurred on one of these 2 data qubits. So you can safely assume that this is not happened instead of no error. So that's what's going on here. Every edge between stabilizer qubit and data qubit, we are taking a syndrome measurement to detect which error occurred in total of the data qubit attached to the data qubit. So for example, here it says that data qubit attached to this stabilizer, there are 4. Among 4, there are either 1 X error or 3 X error. change the eigenvalue of the state to from 1 to 0 or 1 to -1 or -1. So it means that the change has been occurred in odd times, 3 or 1 or 3. So I don't know which one of these, but as long as I find 1 or 3 errors consistent with other results, then we'll be fine. So how about here? So it says that, okay, across this data qubit, the X stabilizer has changed its readoff. That means that it detects on Z error in the nearby data qubit. So the best guess is that, okay, so if you had Z error here and Z error here, then you could detect this way. Like Z error here makes a change on the readoff here. Z error here changes the readoff X here. But that requires 2 errors, 2 data qubits. But that has lower chance than having 1 Z error on this data qubit, which simultaneously changes the readoff between these 2 stabilizing qubits. Right? So your better guess is that there is 1 Z error occurred instead of 2 Z error occurred. So you can guess that this is where Z error occurred. So how about, so we are doing just by eyeballing here. So how about if you have this Z error? How could I have these Z errors? Maybe this error has occurred because of X error here. Then it can only change the readoff nearby Z stabilizer, which is this one. So I can assume that this has been an X error. And how about this one? I can assume that this one has been occurred because of an X error on here. Right? So then it only changes the readoff on this Z stabilizer. But you can do the same thing with different option. So for example, instead of these 2 data qubits have X error, how about we have X error here and X error here? If you have X error here, it changes the readoff on these 2 stabilizers. Right? And if you have X error here, it changes the readoff of these 2 stabilizers. Right? Now, in here, there was 2 changes. So it switched twice. Therefore, you don't detect any changes here. Only the changes occurred at the end. So you still get the 2 X error, possible X errors here. So it's not that you can have more options to have these results. Let's say one option to consider is having X error here, or having X error here. But you could have a different or more unlikely possibility here. For example, you could have Z error, Z detection here occurred by X error on here and here, right? And X error on here. That means you have 3 X error occurred in 3 data qubits. But that's a lower chance than having 2 X error here. So you don't want that. So what we are trying to do is get as smaller data qubit as possible that has an error, that error, that makes this possible. So and then compare that with the result, our simulated result, whether to check whether our error detection has successful or not. So let me show you. I'll explain this again next time because it's there's more to it here. So here we have 2 types of error correction going on in the independent. So in this case, we are trying to correct that. So we are assuming that here this data qubit is where the Z error has been occurred. So we detect this so that when you correct this X stabilizer will turn off. Okay? And here, okay, there's another possibility. Instead of these two, you could have these two data qubits as X. That means if you make X, if you correct X in here, then you can turn off these two changes in the Z stabilizer. Okay, so then you can turn off everything by fixing the errors on here for X error and here for Z errors. Now, let's think about this way. I've done this. I'm assuming that I don't know where the actual error is, but think about our original problem here. Yes, it's true that we have an X error here, right? So we get the correct guess. So we correct the right error. However, we did so about so we saw that there was a Z error. So we thought that we have a Z error here to turn off these two. So we correct it by making a Z gate again, like arbitrarily. So here, Z error. So to fix the Z error, let's say we apply the Z gate on here in this data, cube. But what happens is, it was not really here. It was actually 3 data qubits that has the Z error. So what we actually did is, instead of turning off these 3 data qubits, Z errors on these 3 data qubits, we made one more error intentionally in order to turn off the error, this light. So what we actually have is 4 unwanted Z gates on these 4 data qubits. Okay, so that's what the picture in the bottom says. Here, oh, actually, there was one more on the top, right? There was one more on the top. Here, actually, there was 1, 2, 3, 4 that error instead of 1. But how could he guess that there was 4? Because we could have this result by only 1 error. This is our best guess. But anyway, that was not the actual answer. But anyway, what we have done is we created one more error here instead of turning off these 4 errors. So we have a chain of errors across this boundary to this boundary. Okay. And same thing for X errors. Instead of turning off the real X errors, we actually made another error by correcting error so that we have a chain of X errors. Now the good part of doing this is we didn't fail. We actually corrected error. Why? Even though, so I'm going to discuss this next time again. I'm going to give reason why actually correcting the error. Because we have a chain of error that is going through these boundaries of this boundary. Nothing will happen. Nothing is changed, right? So all the X stabilizers are stabilized, which means that its read-off are not changed. If we have this chain of Z errors, nothing changed. That means whenever you have the same read-off of the stabilizer, it means that your eigenstate, the eigenvalue, is not changed. You are in the same eigenstate as before when you consider all the data qubit as an entire qubit state. So how many data qubits are here? So 10 or something. So 14, and maybe 14 qubit state was in certain eigenstate before, after you apply this chain of errors, you're in the same eigenstate as before, but not maybe not the same eigenstate, but the eigenvalue is the same. Okay, that's the point. You're not changing the eigenvalue of your eigenstate by having these chains of errors. And same for here. The chain is X chain. Now it's run through the left to right. You don't change anything. So you don't change the eigenvalue of eigenstate with the X stabilizer or Z stabilizer. So the whole state, well, if you want to compute the entire tedious quantum state in the vector state, vector form, maybe it's changed, but the eigenstate is being eigenvalue of that eigenstate is not changed. Why is it important? Because what we are doing using this is encoding one logical qubit. This logical qubit depends on whether it's 0 qubit, 0 ket, or 1 ket. It depends on the eigenvalue of the eigenstate. If the eigenvalue of this whole data qubit is 1 plus 1, then we consider it as 0 logical qubit. If the quantum state on this encoded in this whole data qubit has eigenvalue minus 1, we call it ket 1 logical qubit. So we don't care what actual quantum state on this data qubit is. We only care whether that state is in the plus 1 eigenstate or minus 1 eigenstate. These chain of error doesn't change the eigenvalue. That's the point. Okay? So therefore we successfully corrected an error. That's what we are doing here. So I'm going to explain this again if you didn't understand fully about the syndrome measurement and also Ancilla, whatever the story behind here. So, but think about what's going on and just try to write down what you didn't understand clearly and then ask me a question next time.